of the submission things might be messed up, and that could be a problem. But the problems were posted yesterday night, and we have still a few submissions, but we won't go over the problems today because there's no point. Like, most people haven't even seen the problems, so there's no point in trying to like go over the problems now. So what we'll do is we'll go over all 7 problems tomorrow for an extended like beginning session, and then afterwards we'll do the normal stuff. And today we'll have extra time in class to work on all 7 of the problems. So yeah. Okay, if everyone is cool with the plan, we can keep going, I guess. So yeah, so the first topic for today is going to be greedy algorithms. So what is a greedy algorithm? A greedy algorithm is an algorithm which takes like, basically it considers all of the choices that you can make at the moment, and then it just takes the best choice without regard for how that choice may impact future decisions. So for example, let's say that you had an array of a bunch of different elements, and you wanted to find, if you could take k elements from this array, what elements would you take? Well, the greedy algorithm would just go, oh, I'll take the maximum element, and then I'll take the maximum element again, and then I'll keep doing that until I can't take any more elements. And this comes with a lot of pros or cons. So on one hand, greedy algorithms are very efficient and easy to code. So if you just keep taking that maximum element, you can just sort the array and then just like take the last k elements. But they usually do not work. And when they do work, it requires a very intricate proof, especially for harder problems. But for easier problems, you can just think like intuition. You can do it based on intuition. And let's say your program doesn't even work, then you can figure out why it doesn't work. And yeah, so yeah, constructing counter cases is also another way to debunk some greedy solutions. So let's say you had a greedy solution, and then you could construct a counter case. Then I guess your greedy solution doesn't work. Another thing to note is that like if it's really hard, like if you're trying to construct a counter case to your greedy solution and it's really hard to construct a counter case, maybe you should try to prove that actually my greedy solution is optimal, and then think about, oh, how do I prove this greedy thing is optimal? Yeah, but yeah. Okay, if there are no questions, we can keep going. Why should we do greedy algorithms? Because even though greedy algorithms can be are very hardly used to solve problems because they're so like intuitive, but also almost never work. Having that mindset of like, oh, I could do a greedy algorithm, or I could take the best one, but what consequences would that have? It could help lead you towards the solution. Figuring out why your greedy solution does not work, like the bottleneck, why it doesn't work, it can be an important step in solving many hard problems. Like for example, let's say your greedy solution doesn't work because a certain parameter is causing it to malfunction. Then what if you create a separate state for that parameter and you keep track of that parameter throughout the whole thing? Then that may lead to another better solution that would work. So that's just something to keep in mind. So always, like, even if your greedy solution doesn't work, you can get a lot from thinking of it by thinking of why it doesn't work, and like using why it doesn't work to construct your new solution. Yeah. So sometimes your greedy will work, but you'll need some special technique to be able to make it work. It's very common that you need to sort the input or sort something else. And sorting is actually a very common strategy within greedy algorithms, but sorting often requires you to choose the right thing to sort on. So for example, if you're sorting on the wrong thing, then that might be a big problem. So a greedy solution would require you to not only like know that it's a greedy algorithm, but also that you need to be able to implement it. Usually it's pretty easy, but also you need to know like what thing I need to sort on and stuff like that. So one of the most classic greedy problems is the scheduling problem. Basically, the idea is that you have a bunch of intervals. So you have a bunch of intervals. Let's say you have these intervals. You have a bunch of intervals and they're like events that you need to attend, right? So you're given the starting and ending time of each event. And if you want to attend the event, then you have to go all the way from the start to the end. And to travel between events, you can just like treat that as instantaneous. So the problem is asking you, what is the maximum number of events you can possibly attend? Um, does anyone have any ideas about this problem that they would like to share or anything like that? Okay, so a couple people have sent me some ideas. So usually the first thing that you think of is, what if I just like do the most intuitive thing? What if I just take the first event that I can take and then just like keep doing that? Well, let's look at this example that I've already drawn here. If you take the first event, just like the event that just started, then you would take the event at the very bottom, like you would take this event. But taking this event only allows you to take one event in the whole thing. And instead, if you take this event and you take this event, you can take two. So this is already a counterexample to our greedy algorithm. So we can throw this one out. But instead of using the start point, what if we use the end point? Well, if we use the end point, then we would see that this is the first endpoint. And then we would take this. And then we would get rid of these because these start before it. But then you would get this, and then it would work. And if you try to construct a counter case, you'll actually realize that the endpoint is always going to be like the earliest endpoint is always going to be optimal because um like it's the basically like it's the next interval that you're taking. And if you have an earlier endpoint, it's always going to be better than if you have a later endpoint because it allows you to see new intervals. And even if it doesn't allow you to see new intervals, it'll always be at least the same. So it's always going to be better or the same. So you should always take the one that is earlier with like earlier endpoint, if that makes any sense. So yeah. And the way you would implement this is you would basically sort all of them by their endpoint. Like you sort all of the ranges by their endpoint, and then you keep going through and you basically go through the whole thing. If the starting point is before the last ending point that you took, then you just throw that one out. And if the starting point is after, then you just add that one and you update your new ending time. And then you keep doing that. And then you can basically find the answer. Yeah. So yeah, here's a solution. Yeah. So yeah, does anyone have any questions about that? We did go through that very quickly, so if you have any questions about that, it should be um, it should be natural. So yeah, but uh, okay, if there aren't any questions about this, then um, yeah, we'll talk about graphs now. So what are graphs? Well, when you have a graph, you could usually visualize it as like a map with cities and roads. Each node or Each road will connect two cities A and B. And if you look at it, like let's say you draw each city with a circle and you label it with its like ID, let's say it's 1, and then you go here 2, you go here 3, you go here 4. Let's say like you want to like draw an edge between like two cities if there's a road there. So let's say you have edges that look like this. This would be like a graph, right? This is kind of like, this is basically a graph. So each city is known as like a node or a vertex, and each road is known as an edge. And if we like view it as like cities and roads, we can actually figure out some interesting properties about this. So for example, we can call like two nodes that are connected by like a series of roads. We can call that connected because you can get from one city to the other city by traveling through a bunch of roads. You can call you can call a path between two cities to be like a way to get from city A to city B using roads. And yeah, it's actually very easy to like visualize if you think of each node as a city and each edge as a road, because it allows you to have like real life examples of all of the things that are happening on graphs. So for example, like um let's say you wanted to like find the shortest path between two nodes. Well, finding the shortest path would kind of be equivalent to finding the fastest way to get from city A to city B. And visualizing it this way can often help you like find new things, or also just like make an abstract concept more like tangible, more real, and it allows you to like kind of see things. So yeah. Well, I've talked a little bit about what a graph is, but how do we use graphs? Like, let's say you had a graph. How would you even represent it in your code? Well, there are generally two ways to represent a graph: adjacency matrices and adjacency lists. Adjacency matrices are basically where you have a two-dimensional array which stores whether there's an edge between each pair of nodes. So, for example, if you had a graph that looked like this triangle, what would the adjacency matrix look like? Let's say this is 1, this is 2, this is 3. Well, if we use an adjacency matrix, it would basically keep track of whether there's an edge between city A and city B. So let's say we're at city 1. Is there an edge between city 1 and city 1? No, so that's 0. But is there an edge between city 1 and city 2? Yes, so that's 1. Is there an edge between city 1 and city 3? Yes, so that's 1. And then here, is there an edge between city 2 and city 1? Yes, 0, 1, 0, 1, or 1, 1, 1, 0. So this would be like kind of what this adjacency matrix would look like. And this kind of like scales to everything. And this allows you to actually do a lot of cool things with it. Like, for example, if you wanted to go to all of the nodes that are next to it, then you can just go to the adjacency matrix. If it's 0, you just like continue. And then if it's 1, you can go to that node and then do stuff at that node. So it's actually a pretty cool way to represent a graph. However, how much memory does this take? How much time does this take? This takes O of n squared memory, right? Because you're going from city A to city B, right? And there are n cities total, so n times n, which is n squared. Sometimes that's not good enough for a problem. So you have to find another way. And the other way is to use an adjacency matrix. So the other way is to use an adjacency matrix. Or an adjacency list. What would that do? Well, that would store for each node which other nodes it would connect to. So for example, in this case, the adjacency matrix starting at 1 is 2 and 3. So you would write that something like this. And then you would do the same thing for 2. So this would be 1, 3. And then you do the same thing for 3. 1. Now let's analyze how much memory and time this will take. Well, for each edge, think about how many times it appears in your adjacency matrix. If it like each edge will appear once at its first node and once at its second node, right? Because when you're whenever you have an edge, that corresponds to one entry in the first adjacency matrix, adjacency lists, um, like one adjacency, like one element in the first adjacency list and one element in the last adjacency list. So each edge would add two. So in total, you'll have O of M like memory. And that's so much better than O of N squared, because sometimes O of M is really small. Like it's only proportional to O of N, but you also need to do graph queries or whatever on it. And adjacency lists are things that allow you to do that. If you only use adjacency matrices, anything where n is like bigger than 1000 would just completely destroy your code. So adjacency lists are almost always better. However, adjacency lists, as you can see, are probably harder to implement than adjacency matrices. So how would you do that? Well, there's actually a pretty pretty neat way to implement adjacency lists. So yeah. So adjacency lists are like actually not that hard to implement if you know how to use dynamic sized arrays or vectors. So once we use vectors, we can just declare an array of vectors like this. So once we know how to use vectors, we can just declare a global array or something like this. Or let's say max n is 1000. So you could just do something like this. And knowing how to use this is very key to being able to use adjacency lists. So let's go over how to do that. Yeah. So vectors are basically dynamic sized arrays. And basically what they do is you can like add elements to the back, remove elements from the back, access random elements, and do a lot of really cool things with them. So in order to add an element in C++, it's dot pushback. So for example, you wanted to add an element to one of the nodes in your adjacency matrix. So you would just do adj of a dot push back. And then this would basically add B to the adjacency matrix or adjacency list of A. And if you do this for B as well, so add B dot push back A, this will help you add in bidirectional node or a bidirectional edge. And a bidirectional edge is basically a way like an edge where you can go from A to B, and you can also go from B to A, which are most edges in most graph problems. However, you could have directed graph problems, and a directed edge basically is one way. So in order to do that, you can just like delete the last line. So it only goes from A to B, doesn't go from B back to A. So you can just do that. Yeah. To delete an element from the back, you can do pop back, although that won't be very useful because we're never going to use that in adjacency lists. And to access an element, you can do you can basically access it like an array. So for example, in your adjacency list, let's say you wanted to access the first element of your adjacency list at A. So you do adj A, that would basically get that vector. And then you, to access the first element, you do of 0. Yeah. So that's basically how you access the first element of that adjacency matrix. Yeah, does that make sense to everyone? Okay. If so, then we can keep going. So let's talk about some properties of graphs. So these are just two properties of graphs. I could go on and list a lot more, but essentially a connected graph is a graph in which there's only one path between every pair of nodes. Or no. A connected graph is a graph in which there's at least one path between every pair of nodes. So think of it like you have a bunch of cities, a bunch of roads connecting them. And from any city, you can get to any other city using a set of roads. Um, that's basically a connected graph. A directed graph has like edges that only go one way. So like if you have like only one-way streets in your map, then you can only go from A to B, but not B back to A. There's also a lot of other interesting properties. Like there are other types of graphs, like a tree. A tree is essentially a graph of n nodes, which has n minus one edges, and it has a lot of really, really interesting properties. Like for example, each pair of nodes within a tree has one path between them. There are no cycles, and there's a lot of like interesting things you can do with them. Yeah, there's also like bipartite graphs, which is basically like, for example, a bipartite graph is essentially like a graph where a bipartite graph is essentially a graph where you can color each node white or black or whatever coloring you want to do. And once you color each node, no, like there are no like edges between two nodes of the same color. So for example, if you like color this one and you color this one and you color this one, there are no nodes or there are no edges between nodes of the same color, but there are edges between nodes of different colors. And this is called a bipartite graph. And bipartite graphs can have like a lot of really cool properties, um, which are very, very interesting. But yeah, there are also other types of graphs. Like, for example, you can have weights on your edges. Think of like a weighted graph as like, let's say each road it takes a certain amount of time. Like they're not the same length. It takes, some of them are longer and some of them are shorter. So like you could have like weights on your roads. And then once you have weights on your roads, you could do like shortest paths from different nodes. And then you can do a lot of really, really cool things with these. So, but these are just a few interesting graph properties. Does that make sense to everyone? Um, Okay, so now let's talk about the silver portion of the graphs, which is depth first search. So depth first search is a way of traversing through the graph. It basically allows us to search and find values within a graph, and it allows us to do a lot of really cool things. Well, how do you first, like, okay, first of all, how do you do a depth first search? So first, you start at an arbitrary node. It can be any node. It could be zero. It could be n minus one. It could be anything that you want it to be. But then after that, you basically call a function which will process that node. It will mark it as visited. That's one important thing. It'll mark it as visited, and then after you mark it as visited, after you calculate a certain value, then you list all of the children or the nodes that it can go to, and you can do that with an adjacency list. So once you use your adjacency list to list all of the children of that node, then you can basically go to that child. If that child isn't yet visited, then you recurse into that child. And if it is visited, then you can just skip it because you've already visited before. And this guarantees that basically, if you analyze the time complexity here, this guarantees that you'll visit every node once, because if you visited it before, then you won't do it. But if you haven't visited it, then you will do it. So each node, it'll eventually become visited, and there are at most n nodes that could eventually become visited. So it's at most O of n. And when you're listing all of the children, if you're using an adjacency list, the total sum of all of the degrees, which are basically like the number of children of each node, the total sum of all of those like number of children of each nodes, they should be at most m, because like each edge contributes 2 to that sum. So if you do the whole thing, there should be at most O of m, like O of m, like iterations total. So it's O of n plus m. So that's the time complexity of DFS. And this guarantees that you would visit every node in the same connected component once. However, if your graph isn't connected, then it'll only visit like a tiny fraction of your graph. And that's not very good. So there's another way to make DFS even better, and that's flood fill. So flood fill is basically a way to find different connected components. Basically, when you're running a single iteration of DFS, you're able to visit all of the nodes within one connected component. However, if that connected component is not the whole graph and it's only like a tiny fraction of that graph, we can just basically run DFS a bunch of times. So instead of just picking a single arbitrary node, we just loop through every single node. And if it's not visited already, then we call the DFS and we can visit that node and all of the nodes inside that connected component. So let's analyze the time complexity here. The algorithm still guarantees O of n plus m time. Why? Because again, you're only visiting n nodes. So each time you're visiting, you're adding one time. So you have O of n there. But you're also listing all of the children of every node every single time. And listing all of the children takes O of m time for the same reason that I've just described there. So in total, it guarantees O of n plus m time, where n is the number of nodes and m is the number of edges. Does that make sense to everyone? How this works? This makes sense to everyone? There are no questions about this? Um, okay. I guess we can go into our, actually, wait, no. So there are also more applications of DFS beyond just simply graph theories. For example, you're not given a graph, but instead a grid. In these cases, sometimes you can turn the grid into a graph by just like connecting adjacent nodes and basically making all of the basically making all of the individual cells of the grid into nodes and all of the edges of the grid, which are basically like uh like if you think of a grid like this, you can turn all of these into nodes, all of these into nodes, and all of these into edges. And this allows us to use DFS and flood fill on grid problems. And what does this do? Well, let's say you have some parts of the grid are filled and some parts of the grid are not filled. Then you can basically like find connected components which are filled. And that allows us to solve really, really cool problems. Like, for example, the USACO problem, which is on the next slide. So yeah, um, here's the problem. You guys can like open it. Yeah. Yeah, I'll give you guys like a few minutes to think about this problem and then we'll go over it. Oops. Okay, should be back now. Wait, did I send the link in chat? Oh, yeah, I did. Okay. By the way, if you have any ideas about how to solve this problem, you can always like message me directly or even message everyone. Um, as long as your idea doesn't give away too much about the problem, you can message everyone. Yeah. Okay, so does anyone have any ideas about how to solve this problem? Or is everyone just stuck? And if you're stuck, you can also like say like where you are stuck and then like ask for a hint or something like that. But yeah. Okay, so let's actually get started thinking about this problem. So how would we like, first of all, how would we even approach this problem? Because we need to find the area, and it's very hard to like find the area if you don't like do something. So let's try to like turn the grid into a graph. So we can basically have a node wherever there's a grid cell, and for adjacent grid cells, we can have an edge between them. Now, what happens? Well, if you think about it, like each filled component is a connected component. So we can find the area really easily by just finding the biggest size of all connected components. So we run a flood fill, and then we find the biggest size of any connected component. So that's how you do the area part. But how do you do the perimeter? Perimeter is the hardest part about this problem because there's no easy like property about the perimeter. Let's try to experiment. How would we be able to figure out what the perimeter is of a certain figure? So let's say we have something like this. Let's say we have something like this. And this one is filled. This one is filled. This one is filled. And this one is filled. How would we calculate the perimeter of this object? Well, let's outline in a different color all of the edges that will contribute to the perimeter. So this edge will contribute to the perimeter. This edge will contribute to the perimeter. This edge will, this edge will, and this edge will. And this edge will, and so will these, so will these. This one will, and this one will. Okay, so now that we've outlined all of the edges that are connected to our figure, how would we be able to count these edges? And this is actually the trickiest part of the whole problem, because when you're doing something like this, it's often actually very helpful to break it down into components. So let's consider, instead of considering the whole figure, let's consider a single cell. Which of its edges will contribute to the perimeter? Let's say we have this one. We have this cell. Which of this cell's edges will contribute to the perimeter? Well, if it's connected to another cell that's inside the figure, it of course won't. Of course, it won't like contribute to the perimeter. So, what if the edge is not connected to the connected component? Well, if the edge is not connected to the connected component, that means that it's connected to something that's not in the connected component, which is outside. That means that it is part of the border between the connected component and the outside. So in fact, we can just do 4 minus degree, which I'll express with a d. We can basically do 4 minus degree for each node. That's how many edges it will contribute to the perimeter. So now, in order to find the total perimeter, we can just add all of these together and we would get the answer. And the answer would be 4 minus d. So let's try it over here. So here, what is 4 minus d? 4 minus d is 3 here. So 3 plus, okay, what is 4 minus d here? 4 minus 1 is 3 plus, what's 4 minus d? That's 1 plus 3. Which is equal to 10. Now let's double check our answer. Does this work? Well, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, hey, it works. And in fact, based on the logic that I've described, that like each node, how much it contributes to the answer, it should always work. And basically quickly checking on a bunch of small cases, you'll realize that it does in fact work. And once you realize that it does work, then you can just implement the solution pretty quickly and be able to figure out what the answer is. Yeah, does that make sense to everyone? Like how we got from, like basically how we got from having a grid to having a graph, and going from having a graph and being able to find the area to being able to use the same technique to be able to find the perimeter, using a really cool trick of like figuring out how each node contributes to the answer individually, not how the whole connected component looks overall. Does that make sense to everyone? Okay, well, I assume it makes sense. So yeah, let's move on to the challenge problem. So I did promise that we would have more time to do these challenge problems because we were cut short yesterday. So yeah, I've prepared 4 challenge problems for today. There are also 3 challenge problems from yesterday that you can also work on right now. So yeah, these are the challenge problems. They should all be on the Code Forces group as well. So yeah. Also, just as like a side note, you should not try to do the last problem until you've solved the second to last problem, because the last problem is significantly harder than the rest of the problems. So you should try the rest of the problems before you even like attempt the last problem. Yeah, that's just a note. But yeah, I guess the rest of the time is here for you to ask questions about the problems if you're stuck, and yeah, use this time to try to like solve like the 7 problems that